I'd now like to scoop up a few other important topics and limitations under the banner of Other Considerations Part 2. There are several established ways of processing InSAR results, and that's beyond the scope of this course. But one thing they have in common is that they use around 15 or more images to create a network of interferograms, from which, at the very least, a displacement rate and displacement time series are derived. Well-known approaches include persistent scatterer interferometry, or PSI, and the small baseline subset, or SBAS approach, but there are many variations. A key difference between approaches involves how measurable points, or scatterers, are considered. For mining applications, this can have a big effect on the results. Here are the four kinds of scatterers. The two most important attributes are their quote-unquote shape and also how they behave over time. I've ranked them here in terms of their quality, and the first one is a point-based persistent scatterer. So here a single object dominates a resolution cell on the ground, say 3 by 3 meter area, and this might be an area of rock or a building, and the phase value is completely dominated by this object. And this point-based scatterer is also present in every SAR image analyzed. So it provides a very stable or smoothly changing phase return over time. Number two is a non-persistent version of this. So some object dominates over all others within the resolution cell, but something interrupted its continuity over time. Perhaps it was briefly obscured by another object, covered by snow for a period, or was completely changed by mining activity. At a mine, we can expect a lot of this non-persistent behavior, where coherence is interrupted. Perhaps coherence never returns because of continued activity, but more commonly the activity or the event passes and it becomes monitorable again. Whilst these non-persistent scatterers have slightly lower quality than persistent scatterers, they might provide over half of the measurable coverage at an active mine. Number three is persistent over time, but there is no single dominant object in the resolution cell. This we might call a persistent distributed scatterer. Imagine an area of ground with no large solid objects, and this area stays that way throughout the period of analysis. Outside of a city, many scatterers over natural ground will be distributed in this way, and the phase value for these is the sum of the individual phase returns from all of the smaller objects within the area. Because of this, the phase return is a little noisier, and the displacement measurements are again less precise than number one or number two. Lastly, for number four, these scatterers are both distributed and non-persistent in time. So an area of open ground that is one day excavated, for instance. There's still excellent information here. Don't forget that displacement magnitudes at mines tends to be high, so our signal to noise ratio is often very healthy, despite some extra noise from these points. All four of these scatterer types are present at mines, and their relative distributions will vary from site to site. Focusing some more on the persistence aspect of scatterers, the top left image here shows some mining activity over time in SAR amplitude data. We don't use amplitude to measure InSAR displacement, but it is a nice way to see these changes over time. To its right, we see the effect of this activity, the corresponding dark holes created in the coherence images. When the coherence goes dark, there is no InSAR method that can monitor those pixels, but once coherence returns, they become monitorable once more, but as non-persistent scatterers. On the bottom, we see the effects of the activity on two sets of results. The left shows a persistent scatterer only displacement heat map. These scatterers might be point-based or distributed, but they are all persistent in time. And you can see how coverage degrades as activity progresses. Using this method, a kind of processing reset is required at some point to bring back the degrading coverage. To its right, the holes in the results are short-lived because there is no built-in assumption that scatterers must persist throughout the time period. Persistent scatterers are disrupted and then replaced with non-persistent scatterers, and no special action is required. You maintain all of the coverage that it's possible to have. Let's move on now and talk about assessing quality in InSAR. All measurements are subject to some level of uncertainty, and InSAR is no different in this regard. A key benefit of InSAR is its high precision, so uncertainties are often low, quoted at the level of a few millimeters to a few centimeters. It's important to understand the level of uncertainty so you know what to trust. One approach for dealing with uncertainty is, for instance, to assume a global noise floor, say 5 millimeters. Here we would ignore pixels with displacement estimates between plus or minus 5 millimeters and assume those to be unreliable. In reality, though, ground conditions and atmospheric effects will vary from area to area and over time, and the quality of my elevation data might also affect uncertainty differently for different areas. So a global threshold could easily discard some good information where ground conditions for InSAR are above average and retain some poor information where conditions are not so good. So not the best way to handle uncertainty. We need to take account of the varying conditions spatially and over time. Another approach is to look at the scatter of neighboring pixels. We can look at the time series and how different they are. So when neighbors don't agree well, that could be a red flag, but it wouldn't tell us which of those time series are reliable and which are not. And then finally, another common approach is to look at the standard deviation of the displacement over time. Using standard deviation, though, as a proxy for uncertainty implicitly assumes that the displacement is linear in time. Any areas with changing displacement will get flagged as having higher uncertainty, and that includes genuine areas of acceleration. So standard deviation, again, is also a poor indicator of uncertainty. A much better approach is to estimate the noise rigorously at its sources, individually at first, and then amalgamate them into a total noise estimate for each pixel. Things like atmospheric variance or coherence, or also known as surface decorrelation, or topographic uncertainty can all be used for these purposes. This is admittedly a non-trivial exercise because unlike other measurement data sources like GNSS, for instance, there are codependencies in InSAR, and we can't necessarily assume normally distributed independent measurements. But once you build a total noise map, you can use that and compare it to the measured displacement signal to arrive at a signal to noise estimate for every single pixel. Let's look at other examples of this SNR approach to uncertainty. If I, for instance, have 4 centimeters of measured displacement and 2 centimeters of measured noise, 4 divided by 2 equals an SNR of 2 standard deviations, which is equivalent to 95% confidence. 95% is equivalent to a 1 in 20 chance that a given area of noise would produce a displacement detection. For a large area, we might expect to see a decent number of false positives with that kind of statistical cutoff. 4 standard deviations, on the other hand, which is a more commonly used cutoff for displacement detection in mining, provides a 99.99% confidence level. This means that any given area of noise has only a 0.01% probability of producing a detection like this due to chance alone. The agreed cutoff threshold of 2, 3, 4 or higher standard deviations could be a user choice depending on their tolerance for false positives. A dam with unexpected but high consequence displacement might adopt a lower threshold and therefore let in more false positives because they need to be really sure of those edge cases. A really dynamic stockpile, on the other hand, might have a higher threshold because we expect it to move, but the risk of failure is less consequential, and we don't want to be bothered with lots of false positives. On the left side of this slide, we see how the SNR is affected by different levels of displacement and noise. And on the right, we see contours drawn around areas of displacement. These contours circumscribe areas at or above the agreed signal-to-noise cutoff. Once there is a good understanding of the noise in a dataset, a system like this is effectively self-regulating. It adjusts based on the changing environmental conditions for InSAR. In areas where noise is low, contours will circumscribe more subtle displacement estimates. And when it is higher, it will automatically be more conservative because displacement estimates have more noise to overcome in order to be classed as significant. So if the goal is to provide the earliest possible alert for a new potential risk, then this approach will do that. Lastly, let's consider again those really dynamic areas where displacement is expected and mostly mundane. SNR-based contours will help us to narrow down what to pay attention to, but we still kind of have a big data problem on our hands here. We're getting updates every few days, and each update shows the same high confidence displacement area. But so what? How will I know when to really pay attention? In these situations, we can instead focus on changes in displacement. By comparing statistically reliable periods of displacement, we can detect areas of acceleration, which should be much rarer than mundane linear displacement. The slide here shows that comparison on the left. The green period is being compared to the orange period, and their relative distributions are distinct and different. These are areas that should really draw our attention. On the right, we see a displacement heat map annotated with purple SNR contours, but also shown are some smaller yellow areas which indicate recent accelerations. This then is a good solution to our big data problem because there should be far fewer of these areas to consider and investigate.